Let's do something more practical. So what we have covered so far are essentially new rules for physics, because all the mechanics, everything that we have worked out was assuming what's called the Galilean relativity. It's assuming, when you're comparing two moving things, that their coordinates vary, like x prime is equal to just the x minus beta ct, no gamma factor here. And it's assuming that the time was some absolute time. So there being this new set of rules that have to be now obeyed, it means everything in physics is going to change. In fact, you can divide all of physics into two categories. Physics that's relativistically correct. That's, I guess, you have learned only one piece of physics that's relativistically correct. Believe it or not, you actually know something that is relativistically correct. Anybody here know?
Conservation law.
When you say conservation law, I mean, it depends on what are you trying to conserve. So energy is an abstract quantity. It's a calculated quantity. So if you are trying to say, energy is conserved, if you are using your non-relativistic expressions, then it won't be correct. So the idea that energy is conserved is still correct. But it's like with the idea of principle of relativity. That's still correct. But if you're using Galilean relativity, you'll be wrong. If you're using special relativity, then you'll be right. But there is some very specific mathematical form of law, physical law, that that's actually relativistically correct.
I remember you told us the definition of force is always correct.
So this is what I say in physics 4a. So in physics 4a, you are initially told force is equal to mass times acceleration. And halfway through the semester, I tell you that I lied. And this is not actually correct. Anybody who wasn't in my class know what the other form of force is that's more correct than this? Anybody who wasn't in my class? So, function? You should know a second form of force that you were told. Maybe you weren't told that it was more correct. Genkai? Second form of force relates to impulse. Relates to something called the impulse. You don't remember? All right. So the second form of force that's useful for you to remember is force as the time derivative of momentum. Does that ring a bell? That force is time derivative of momentum? Yes? Well, all right. And this is the more correct expression. But here's the thing. The expression for momentum that you have so far is mv. And that's going to be wrong. So you have to have the correct expression for momentum. There's only one piece of law of physics that you know, that you don't have to correct a single thing, because it was relativistically correct from the beginning. You just didn't know it was relativistically correct. Yeah, Maxwell's equations. Theory of electrodynamics is the only piece of law that you know that is actually relativistically correct. So when you divide all the laws of physics, there's the relativistically correct laws of physics, which over which you know exactly one, the theory of electrodynamics. Historically, it makes sense, right? It's in considering laws of electrodynamics that we stumbled upon law of special relativity. So those two just start out agreeing with each other. And the rest of the physics that you learned, they are not relativistically correct. They are the low-speed approximations. So now what we have to do is we have to rework every single piece of physics so that it's consistent with this. And there's quite a bit that we won't do. In fact, the correct expression for momentum, I'll just give you the answer. I won't derive it. I decided before the class started that I won't have enough time to do that. But let me derive the relativistically correct the kinetic energy. So this is the task that we are embarking on. We are embarking on redriving every single law of physics so that they now agree with this. well, we won't do it for every single one. We'll do it for the ones that we matter to us, and we're going to be using it. But this is the mindset that you have to have, that every single law of physics, with the exception of electrodynamics, was non-relativistic. So you have to it's like, this is very fundamental shift in what we think about physics. So there's going to be a necessary changes that come from this. So every single aspect of physics, other than just general principle like conservation of energy, principle of causality. So other than very general principles, any specific formulas, you are going to have to rework them so that they are consistent with this. So the very first casualty, or I guess very first item on our to-do list is energy. And that might end up being the only one because it's the only one that's easy enough to do in one class session in like 5 to 10 minutes. So you have, so conservation of energy is still going to be correct, provided that you define energy in a correct way. So, so overall, the forms of energy, let's just focus on one, kinetic energy. So in physics 4A, you were told, or depending on the instructor, you saw derivation of kinetic energy as 1/2 mv squared, right? And at least this is the way I do the derivation in my class. I assume a constant force. So I assume some. So this is what is claimed as the general formula that applies in every single situation. What that means is if I come up with a very special circumstance, then the formula that I derive for the special circumstance will still be correct in the general sense. It's sort of reversal proof. Anyway, so that's what I do to kind of guess at that formula. Imagine you have some object of mass m, and you are applying some constant force F. And I guess the result of that is that it's accelerating according to F over m, right? And as it's accelerating, oh shoot. I swapped this order. I don't know if that works. Should have done this before. Let me just finish this sketch. So it has that acceleration. And there's a kinematics that you learned. And the kinematics is, so this is, if this is constant, then acceleration is constant. You learned a bunch of constant acceleration kinematics formulas. One of them is this one, the V squared formula. The V final squared is equal to V initial squared minus plus 2 times acceleration times delta x. So, so everyone remember all these little pieces? Yes? So what we did was, all right, so the thing that we are going to call kinetic energy, we are going to say it comes from the work. So the change of any time you want to change energy, it involves work, right? So here, your work being done is force times this displacement. So you say, all right, work being done. So this is going to be the change of kinetic energy. That'll be force times delta x. So I look at this expression here, or let's see, how do I put it? I have this. I guess one way to combine them is to solve this for, or actually plug this acceleration into here. Then what I would get is vi squared plus 2 times f over m times delta x. So I look at this as work. So I solve this equation for work. The result of that is V final squared minus V initial squared multiplied through by m over 2. So that's the change in energy. Let's say you are changing kinetic energy from 0. Then your initial velocity, initial speed was 0. So your final kinetic energy is 1/2 times mv squared. That's what you have here. Okay? So that's how we derive the kinetic energy in physics 4a. It starts out with this idea that the change in kinetic energy is the work done. You used Newton's second law in the process of doing that. And I guess that's it, because kinematics is just math. So what I'm telling you now is that all these general steps are still correct. The idea that changing kinetic energy is the work done, that's still correct. You could call that the principle of energy conservation. Or you are trying to define energy in such a way that whatever work you are doing leads to energy being changed somewhere. So this step is correct. Let's see. Are the kinematics correct? So I guess by kinematics, this is what I mean. So acceleration is defined as dv dt. Velocity is defined as dx dt. Are these correct? I mean, is in the special relativity, is velocity still rate of change of position? Right? Velocity is the rate of change of position. Like, how else would you define it? Is acceleration rate of change of velocity? Yeah, acceleration is the rate of change of velocity. I mean, I keep saying in my classes, kinematics is not physics, it's math. And that's what I kind of mean. I mean, these are the mathematical definitions, and like there's no law of physics that tells you that, but that's how you would define it. And that intuition doesn't change yet. So velocity is still defined this way. Acceleration is still defined this way. Now, this is the piece of step that is incorrect, and that forces the rest of the change we are going to make. This piece of step, this came from Newton's second law, right? The force is mass times acceleration for constant mass. And nothing you did in physics 4a, made you change that. For constant mass, even with this, for constant mass, force is still mass times acceleration. What I'm telling you now is this is wrong. That's based on non-relativistic physics, and even for constant mass, even for an object that has mass that doesn't change, this will no longer be correct. So if you are saying force F is equal to ma for constant mass, then I'm telling you now, no, not anymore in physics 4c. But what will still be correct is this. The force, we can still define it as rate of change of momentum for the correct definition of momentum. And actually, let me take a little, sorry, I know in your textbook it's done the other way. I swapped the order thinking I could do just the relativistic energy derivation without needing relativistic momentum. Let me just think this through to see if I can actually do that. It's possible that so this portion is still correct. Work is still defined as force times displacement. So yeah, it looks like, so if I'm going to talk about force, then I actually need this. If I'm going to talk about this, then I need the momentum. So, so it looks like I didn't quite think things through. So let me give you some answers that I'm not going to derive. I may write up a note because I happened to glance at your textbook and I don't like how your textbook did it, which is, I think, the same way Giancolli does it. So anyways, so let me just give you the answer from the textbook that we are just going to use. And the reason I wasn't going to derive this was because this is one of those cases where the answer is much simpler than the derivation. So this is the answer that I'll show you from the textbook. The relativistically correct expression for momentum it turns out to be remarkably similar to the momentum you already know. What's the expression for momentum that you already know?
Mass times velocity.
Yeah, mass times velocity, right? And to make this relativistically correct, all you need is a factor of gamma. That's it. Where gamma is, I guess, based on that v. So gamma sub v. That's it. Or, writing it all out, it would be mv divided by square root of 1 minus. And if I'm being really, fastidious and careful, v is a vector. So let me write v squared this way. V added to itself divided by c squared. That's the relativistically correct expression for momentum. And so this is how your textbook does it. I looked at it, and when I looked at it, I didn't like it. But just so you know, I'll just show it to you so that it's, I guess I do have to switch this order. Sorry, you can't do energy without knowing momentum. And the derivation that I prefer is based on collisions, because here's the thing. So it comes down to the fact that the special relativity is, this is a jargon in like a philosophy of science. Special relativity is paradigm shifting. It changes, it's not just telling you a formula that you didn't know. It changes the entire way of thinking. And it ought to change the entire way of thinking. Otherwise, you're going to have patchwork of stuff that's going to appear contradictory. So special relativity changes your entire paradigm of thought, or at least it's supposed to. And all your textbook does is it's doing momentum is this, where all it changes is this time. And I feel like it's not the correct foundation to build it on. My preferred derivation of this involves analyzing a collision. Because in analyzing a collision, you are essentially assuming only two things. You are assuming conservation of energy, and you're assuming conservation of momentum. So even though Newton's second law is wrong, you are saying Newton's third law is still correct. And so let me see if I can write up a note based on that. But for the rest of today, we'll just take this as the correct answer, which it is, and just proceed based on that so that we can do the rest. Okay? So all right, so with that out of the way, let me try to finish this derivation of relativistic energy. So I feel like I have all the pieces I need. So I still have this piece. So in deriving kinetic energy, I'm going to use the idea that kinetic energy, it comes from the work being done, which I'm going to write down as F times delta X. And I will say I'm still going to apply constant force F. Okay? All right. Let's see how far I can get before I'm forced to do a couple things. So let me. So I'm going to be careful with each expression I write down. I'm going to be testing, is this expression valid under special relativity? So derivation of relativistic kinetic energy. All right, so let me start out from here. So I'm going to just say my kinetic energy, it's going to start from 0. So my kinetic energy that I will reach, starting from 0 kinetic energy, is equal to the work being done, or force times delta x. That is, let me draw this picture here. I have some object of mass m, which has initial velocity of 0. I'm going to apply a constant force of F, which will, it'll cause it to accelerate, right? Yes, so it'll cause it to accelerate. It's probably not going to accelerate like this, but it'll still accelerate. And after accelerating for a while, it'll reach a position. And I can measure how far it moves, delta x, or how far it moves, that's related to its acceleration. And so this had the kinetic energy of 0 here. And here at this position, as it's moving at some speed, it has some kinetic energy of final kinetic energy. Good? And I'm trying to come up with an expression for this final kinetic energy. Now, before, the nice piece I had was the expression for acceleration. And what I'll tell you now is, now I don't. In fact, let me see if I can, well, let me see how far I can get before I have to write down, start driving some stuff. So, let's see. So I cannot use what I used before because I'm trying to rewrite this in a way so that it's not in terms of force. Because force is a dynamical quantity. I want something that's kinematical, position, velocity, acceleration. So I'm going to look back at this expression because this depends on this is only tied to Newton's third law, the conservation of momentum being related to the action-reaction force. So I'm still going to rely on this. And relying on that, I can express a force, F here, as that, time derivative of momentum times delta x. And this is where I would now need the expression for momentum. So using that expression for momentum, I would say this is equal to time derivative of gamma mv times delta x. Let's see. Can I go through this? Well, I guess I should write this out as in terms of using the method that I do know. So this is product of three things, two of which are variable. Gamma is a variable, V is a variable. Or gamma is a function of V, right? So just going through the math, what this looks like is equal to, I use product rule. So mass times derivative of gamma with respect to t times v vector plus gamma times derivative of v dv dt. So that's that derivative there times delta x. I guess it's dot product technically. So this is the question I want to pose. That the question I want to pose is this: are we dealing with a constant acceleration kinematics? So here, I can still say this is acceleration. Right? That's the definition of acceleration, time derivative of velocity. Now, the condition I can impose is that the force is constant. Now, if the force I'm applying is constant, do I have a guarantee that this acceleration is constant? Is it? Look at it carefully. So this term can only be constant if as the velocity changes, if this doesn't change, and if this doesn't change, or they change in some combination to guarantee that this one term, out of 4 or so terms, one have to change. Does that seem likely? Yeah, so that's the very first thing to go out the window. That you have to abandon this idea of this constant kinematics applying, because it's not. It's just not going to be a constant kinematics situation. So this is where I'm going to have to take a step back. Instead of trying to calculate work as force times the distance, do you remember a similar situation in physics 4a where you couldn't just calculate work as force times distance?
When the force keeps changing.
Yeah, when you have spring force. Like that's the situation where we introduce variable force. When you have spring force, you couldn't say force times distance, because which force? It changes. So that's where you had to set up the Riemann sum, or breaking up this entire motion into tiny little pieces. You can say for each point on the motion, force is some amount, and force times the tiny little portion, and then add it all up. What mathematical representation represents that? Integral, right? So I have to do the same thing here. I have to say, all right, I can take the whole thing all at once. I have to say my work done is going to be the force times dx integrated from x equals, 0 to some final value. So that's what I'm going to have to do here. So let me erase all of this, because this is sort of going down the wrong path. It's not really getting me what I want. So let me come back to here. So this was just useful for us figuring out that acceleration is not going to be constant. So we have to abandon one more of the ways we were doing things before. So we have to say, all right, so it's going to be an x integral from 0 to some final position of the force. So that's so we'll write down the same thing as before, time derivative of momentum. So I remember being able to do this in some very simple steps as long as I knew what I was doing. So I'm pretty sure I don't need the integration by that. Okay, so let's say this is equal to x going from 0 to x final. And so time derivative of, so gamma, and I'm going to make it one-dimensional. So my force is going in the same direction. So it's being applied in one direction. So my eventual velocity will be in the same direction. So it's just one-dimensional. Gamma mv times dx. And so this is the exact right step I remember doing before. I'd like to re-express some things here. So gamma and v, they are actually a function of one and the same thing. So here, you saw me express gamma in terms of v. You can do it the other way. You can do it as, so this is the expression. Gamma is equal to 1 over square root of 1 minus v squared over c squared. I can solve this for v. Let me just quickly do that. I've written it down once before, but let me do it quickly so that you are not doubting my memorized formula. So square both sides, take the reciprocal, then what you end up with is 1 over gamma squared is equal to 1 minus v squared over c squared, right? So move this over. So you have 1 minus 1 over gamma squared. That's equal to v squared over c squared, which means v is equal to c times square root of 1 minus 1 over gamma squared. Right? That's an expression I've written before. And the reason I have that expression memorized is because of how useful it is. So let me plug this in for v. So I'm doing something that's a little bit unusual. For a lot of people, the intuition you have when you're doing algebra and calculus with the special relativity is to solve things in terms, cast everything in terms of V. I'm telling you now that in special relativity, often the gamma will be the more correct variable to use. So let me do that now. So plug this in for V. This is what I end up with. So I have the outside the shell still. So inside is time derivative. Let me just pull the m out. M times the time derivative of, so gamma times V. So gamma times all of this. Let me absorb gamma into the square root. Then I get C times square root of gamma squared minus gamma squared times that, 1. Yeah. Times dx still. Am I ready to use? All right. I guess, yeah, so let me, okay, so this is looking a lot simpler than what I was facing before. Before I was thinking of using product rule, and a lot of that looked complicated. So, I wanted to, what I remember of the correct steps is I wanted this integral to be in terms of gamma instead of x as my variable. I'm not quite sure how to get there. So I might have to write it out first. Let me write it out. Maybe then it'll be clearer. So it's still going from x equal to 0 to some final position. So I'll have to do this derivative now. So it's mc times derivative of this with respect to time. So 1 over square root of, it's actually 1/2 times what, so what this is. It's 1/2 times 1 over square root of, let's see. Let me do it on the side and then I'll copy down the simplified version. So I'm doing this derivative with respect to time of square root of, or let me rewrite the square root. It's gamma squared minus 1 raised to power of minus 1/2. So then it's just a polynomial derivative. So it's this factor down, minus 1/2 times, not minus, sorry, just the 1/2. So it's polynomial derivative. So 1/2 times this raised to power of that minus 1. So gamma squared minus 1 raised to power of minus 1/2. That's the outside derivative. Chain rule, I have to do the inside derivative. So it's 2 gamma times 2 gamma times, gamma is still a function of time. So time derivative of gamma. All right, so the simplified version is this 1/2 will cancel out with the 2. Kind of didn't want to write that down. So I have gamma over this times that. So let me write it down. It's gamma divided by square root of gamma squared minus 1 d gamma dt times dx. Okay? Wonder, so I have integral with respect to x. The thing is, I don't really want to relate this to x. That gets complicated. Let's see. I think this might be where I
If B is dx dt,
yeah.
you replace right? And then if you have your expression for v, you have dx is equal to c times that term.
Yeah. All right. I guess we will abuse the notation that way. Yeah, I'm sure that'll lead to correct result. Yeah. So don't tell your math instructors that we did this. This is actually quite common practice that's known in physics community as abusing the notation. So this is what this looks like. It's d gamma times dx over dt. And what I'm going to do is I'm going to say, all right, that looks like a fraction. So let me just put that denominator over here and say that this is dx dt. Oh, that's my velocity v, which is, according to this, equal to c times square root of 1 minus 1 over gamma squared, right? Now, all of if that sounds good to you, then fine. The result it leads to is the correct result. So let me do that. It's called abusing the notation, and it comes down to we are just taking a shortcut to get to the correct answer more quickly than a mathematician would. Yeah, so thank you for the suggestion. Let's do that. So what that has done is I no longer have integral with respect to x. I do have integral with respect to gamma. And what this abuse of notation hasn't taken care of the integration limit. So we'll just have to imagine that we are taking it from some initial gamma to some final gamma. We'll figure that out later, what those initial and final gammas are. Okay? All right, so that's good enough. All right, so let me clean up that expression there and write down an expression that's correct here. So I have mc squared, right? Let me factor that out. So I have mc squared times the remaining integral. It's going from some initial value of gamma, we'll figure that out later, to a final value of gamma. And I have gamma times that. So let me write that out first, and then we'll simplify. Gamma times the square root of 1 minus 1 over gamma squared over square root of gamma squared minus 1 d gamma. Now we get a wonderful simplification here, which is why I remember doing integral with respect to gamma was the correct way to go. Absorb this gamma into the square root. Then you get gamma squared minus 1. Hey, that's the same thing as this one. So I can cancel that out. This is actually proper algebra. It's not abuse of any notation. But what you have remaining is just the d gamma. There's nothing else here. You know how to take that integral. That's just gamma. So this integral becomes gamma evaluated from initial gamma to the final gamma. What's the initial gamma? So initially here, we started out at 0 velocity. So what's a gamma that corresponds to 0 velocity? 1. Yeah, 1. And the final gamma is whatever gamma you end up with. So let's just call that gamma. So what this all simplifies down to is this. All this simplifies down to mc squared times the final gamma minus 1. So this is the expression for relativistically correct kinetic energy.